Hey OChem Ninjas, here is a single mass spec, no IR, no NMR. Can you give me 3 plausible molecular formulas that would fit this spectrum without being provided with any other information? Stay tuned for the 13-second trick that's so brilliant it feels like cheating. As you go through organic chemistry, you're going to learn about mass spectrometry. In this video, I want to teach you a deceptively simple trick that will allow you to extract a list of plausible molecular formulas, even if the only thing you have is a mass spec and nothing else. Now, when I teach mass spec to my students, I tell them you probably can't solve an entire structure just from a mass spec. And I generally think that's true. In fact, I tell my students you really shouldn't spend more than 30 total seconds analyzing the mass spec before you move on to other spectra. If you'd like to learn how to only spend 30 seconds on mass spec, or if you need to brush up on spectroscopy in general, I have a link to my entire spectroscopy playlist down below. In order to solve a structure from a spectrum, you really need a target to aim at. You really need to know what the molecular formula for the molecule could be. A lot of the times, instructors will give you the molecular formula for the molecule you're solving. Sometimes you might only be given elemental analysis data from a combustion analysis experiment. And if instructors are really pushing you in your spectroscopy studies, we may not give you a molecular formula at all. If that's the case, the first thing we want to do is this rule of 13s on our mass spec to get a list of plausible molecular formulas. The rule of 13s is predicated on the fact that we are, in fact, organic chemists. And that's more than just a warm, fuzzy affirmation. It actually means something for the rule of 13. If you were looking at a molecule that was not an organic molecule, the rule of 13s wouldn't really apply. The rule of 13s is predicated on a simple proposition that every organic molecule contains carbon, and there's at least one hydrogen per carbon in that molecule. The atomic weight of carbon is 12 AMUs, and the atomic weight of hydrogen is 1 AMU. If we add those up, the rule of 13s is predicated on the foundation that molecules are made up of multiples of 13 AMU units, a series of carbon with at least one hydrogen per carbon, plus some other atoms to get the entire molecule. We'll talk about those in a second. Let me clear up one tiny misconception here at the beginning. This set of basic assumptions does not mean that every carbon needs one hydrogen attached. The rule of 13s doesn't say anything about the structure or its connectivity. There may certainly be quaternary carbons or alkynes or benzene rings where some of the carbons may have 0 hydrogens attached, but there will be other carbon atoms with 2 or 3 hydrogens attached, and so the theory is that there's at least a 1-to-1 ratio of hydrogens to carbons plus a few extra. Using these assumptions and the rule of 13s, we can come up with a list of plausible molecular formulas for this structure. Most of those will not be the correct formula. There can only be one correct formula, but for most simple sophomore organic structures, the molecular formula will likely be in your list somewhere. All right, so what is the rule of 13s? How do we do this? The first thing we need to do is find the molecular weight of the molecule from this spectrum. This isn't a video on how mass spec works or how to read a mass spectrum. If you need to brush up on those, I'll refer you to my spectroscopy playlist linked down below. But in general, for most organic molecules, the tallest peak in the cluster furthest to the right is typically the molecular mass for that molecule. So for this molecule, the M+ peak would be at 86 AMUs. Then we divide the molecular mass by 13. Yes, I'm talking elementary school long division with a quotient and a remainder. You do remember your 13s times tables, don't you? You likely won't get to use your calculator on the exam, so it may take a little guess and check to figure out that 13 goes into 86 6 times. Finish out the long division. 13 times 6 is 78, and 86 minus 78 gives us a remainder of 8. Don't worry, friends. Dividing by 13 is the hardest math you're going to be doing in the entire course of organic chemistry. I believe in you, ninjas. I know you can handle it. And this answer to this long division problem gives us all the information we need to find a list of plausible molecular formulas. The quotient of 6 tells us that there's 6 CH units with an atomic mass of 13 AMUs. So the quotient of 6 tells us that there are 6 carbons in this possible molecular formula. And the remainder of 8 tells us there's 8 more AMUs in this molecular formula. We can take those 8 remainder AMUs as 8 additional hydrogens in the molecular formula. We add those 8 hydrogens to the 6 hydrogens in our 6 CH units to give us a total of 14 hydrogens in this molecule. The quotient plus the remainder gives us the number of hydrogens in this plausible molecular formula. There you go. There's one plausible molecular formula for this molecule. You can double check your work. 6 times 12 is 72, plus 14 more gives us 86 atomic mass units, just like the M+ peak in our mass spec. And this would be great if every molecule was a hydrocarbon. But what if there are heteroatoms in the molecule? How do we account for an oxygen or a nitrogen in this formula? We cannot just stick an oxygen on the end of this formula, C6H14O. Can you figure out why we can't just append an oxygen? An oxygen has an atomic mass of 16 AMUs. We already have our 86 AMUs. If I add another 16, now that molecular formula would have an atomic mass greater than what this mass spec says. So if we want to add in an oxygen of 16 AMUs to this molecular formula, we have to take out an equivalent unit of 16 AMUs from the original molecular formula. Can you think of some combination of carbon and hydrogen that could add up to 16 AMUs? A CH4 unit adds up to 16 AMUs. So if I want to add in an oxygen to this molecular formula, I have to swap out those 16 AMUs for a 16 AMU fragment from the original molecular formula. I need to subtract a CH4 group. That gives me a second plausible molecular formula of C5H10. Oh, again, you can check your work. 5 times 12 is 60, plus 10 is 70, plus 16 gives us 86. So C5H10O is a second plausible molecular formula for this structure. Isn't this amazing? Another sanity check you can do at this point is to calculate a quick index of hydrogen deficiency for these molecular formulas. Make sure they make sense. This isn't a video on how to calculate index of hydrogen deficiency. I know every instructor has their own formula they like to use to calculate IHD. I have a formula that I think is really intuitive for students, and I'll link to that video down below. But the IHD for this first molecule would be 0. And the IHD for the second molecule would be 1. Isn't that interesting? For the same atomic mass, swapping in an oxygen increases the index of hydrogen deficiency by 1 unit. But what if, say, my IR spectrum tells me that I really have 2 oxygens? What should I do then? I can do the same thing. If I want to add in a second oxygen, I need to swap out another 16 mass unit equivalent CH4 group. If there are 2 oxygens in the molecule, then the molecular formula is C4H6O2. Again, we can check our work. 4 carbons is 48, 2 oxygens is 32. 48 and 32 get us to 80, and 6 more hydrogens gets us back to 86. So C4H6O2 is a third plausible molecular formula for this structure. And continuing with our newfound pattern, if we calculate the degrees of unsaturation for this formula, we find that it has 2 degrees of unsaturation. But what if our IR says it's not an oxygen in our molecule, but a nitrogen instead? How would we add in a nitrogen into this formula? If I think there's a nitrogen in this molecule and I want to add in a nitrogen atom, I need to swap out an equivalent set of mass units. Nitrogen's atomic mass is 14 AMUs. So if I want to swap in 14 AMUs, I need to swap out an equivalent mass of 14 AMUs, a CH2 group. If I think there's a nitrogen in the molecule, that gives me a new molecular formula of C5H12N. 5 times 12 is 60, plus 12 is 72, plus 14 gets us to 86. So we could consider C5H12N as a plausible molecular formula. But if we do our quick sanity check and check the IHD for this molecule, the index of hydrogen deficiency for this molecule is 1/2. And if you recall from your IHD lesson, we can't have a fractional index of hydrogen deficiency. That ultimately means this is not a valid molecular formula for this structure. And that should make a bit of sense if you recall from the mass spec unit that a nitrogen should give an odd M+ peak in a mass spec, and we have an even M+ peak. But we could consider 2 nitrogens. If I want to add in a second nitrogen in the molecule, I need to subtract out an equivalent CH2 group to get 14 mass units. That gives me a new formula of C4H10N2. 4 times 12 is 48, 2 nitrogens is 28, that gives me 76 AMUs, plus another 10 gets me to 86. So we can consider C4H10N2, and that should make a little bit of sense. An even number of nitrogen should bring us back to an even atomic mass. And a quick index of hydrogen deficiency check here gives us an IHD of 1. Isn't that interesting? Swapping in a nitrogen for an equivalent atomic mass increases the IHD by 1/2. But what if the rest of our evidence in other spectra tells us that there's both nitrogen and oxygen in the molecule? I mean, I could just keep going with these substitution games all day long. We can do this as many times as necessary. To bring in an oxygen atom, we would need to subtract out 16 atomic mass units, our CH4 unit. That gives us C3H6N2O. 3 carbons is 36, and 6 hydrogens is 42. 2 nitrogens is 28. 42 and 28 gets us to 70, and 16 gets us to 86. So we'll finish out this exercise with C3H6N2O. And fitting with our other patterns, this has an IHD of 2. So how do you like that, folks? With not that much effort, we came up with 5 plausible molecular formulas from a blank mass spec with no other context. Which one's the right one? I have no idea. Well, okay, of course I do. I picked this mass spec, I know what the structure is. But the point is, this gives you a bank of molecular formulas that you can use as a checkpoint as you start to build out other structures. Test them against these molecular formulas, see if they fit. Here's another pro tip for free. Look at your proton NMR and add up the integration values. For nearly all molecules, the sum of the integration values in the proton NMR should be the number of hydrogens in the molecule. And if you add up the integration values, it should match up to maybe 14 or 10 or 6, and that can help you narrow down this list even further. You can kind of do the same thing with carbon NMR, but because of symmetry, the number of carbon signals may not always line up with the number of carbons in the molecule. But if there are 6 peaks in the carbon NMR, it can't be something with 4 carbons in it. When I teach my students mass spec, I like to tell them mass spec doesn't tell us a whole lot, it just gives us context within which we can analyze the rest of the spectra. And this neat little trick certainly fits in that category. Let me run through another worked example fairly quickly without much commentary so you can see it in action again. The molecular weight looks like it's 121 divided by 13. 10 would be 130, so it must be 9. 13 times 9 is 117, which gives me 9, remainder 4. Now, a molecular mass of 121 is already starting to ring some bells in my head, but let's go through with the analysis. The straight results from the rule of 13 tells me there's 9 carbons, and 9 plus 4 equals 13 hydrogen. Remember, the remainder isn't the number of hydrogens, it's remainder plus the quotient that gives you the number of hydrogen. But actually, this gives me an IHD of 7/2, so I know that this actually can't be a molecular formula for this structure. An odd M plus peak makes me think nitrogen, so if I want to add in a nitrogen, I need to subtract out 1 carbon and 2 hydrogens. This formula brings our IHD to 4, so this could be a plausible molecular formula. To play around with other combinations, if I think there's also an oxygen, I'll take out 1 more carbon and 4 more hydrogens and add in the oxygen. That gives me C7H7NO with an IHD of 5. And if I think there's a second oxygen, that would bring me to C6H3NO2 with an IHD of 6. It's really amazing how much information this gives you. When you turn the page on your exam and there's a mass spec and that's all you see and you've got nothing to work with, this gives you so much more context. When it feels like there's nothing to hold on to, this is a place to start. Let's look at one more wrinkle before we close for the day. What if your mass spec tells you there's a halogen in the molecule? Halogens are one of the easier things to spot in a mass spec, so if I think my molecule has a bromine in it, I'll have to include that in the formula. We've been talking about running the rule of 13s and then adding in the heteroatom and subtracting out an equivalent mass unit, but on the periodic table, bromine's atomic mass is 80 AMUs. How many carbons and hydrogens do we have to add together to get 80 AMUs? I wouldn't do it that way. I would actually reverse things a little bit if you know there's a halogen in the molecule. The first thing I would do is subtract out the halogen from the molecular mass of the M plus peak. For this molecule, we have the M peak at 122 and the M plus 2 at 124. How do we know which one we're supposed to use, and how do we know which isotope of bromine we're supposed to subtract? It really doesn't so much matter as long as you are consistent. Recall that the 2 naturally occurring atomic isotopes of bromine are bromine 79 and bromine 81. The molecules that randomly have bromine 79 will give rise to the molecular M plus peak at 122, and the molecules that happen to have bromine 81 will give the M plus peak at 124. So we can either subtract 79 from 122 or 81 from 124. Doesn't really matter as long as we're consistent. For me, personally, subtracting 81 is easier than subtracting 79, but they should both give the same answer. So 124 minus 81 is 43 AMUs, and then we can run the rule of 13s on this new atomic mass without the halogen. 13 goes into 43 3 times. 13 times 3 is 39, which gives us 3, remainder 4. So from the rule of 13s, we get a plausible molecular formula of C3H7, but that's not really the molecular formula. This only adds up to 43, and that's not what our M peak shows. So once we run the rule of 13s on the molecular mass without the halogen, we can add the halogen right back in on the end without missing a beat. By appending bromine on the end, C3H7Br does add up to our M plus peaks, and C3H7Br has an index of hydrogen efficiency of 0. And then we can still do all of our other manipulations. If we think there's an oxygen, we can take out 1 carbon and 4 hydrogens and add in the bromine and the oxygen. And this would give us an index of hydrogen efficiency of 1. So if there's a halogen, subtract it out first, run the rule of 13s, append it at the end. Let's do one last example to show how it works with chlorine. Again, I would recommend subtracting the halogen out first before running the rule of 13s. Recall that the naturally occurring isotopes of chlorine are chlorine 35 and chlorine 37. Subtracting 35 from 154 gives us 119 AMUs. 13 times 9 is 117. That gives us 9, remainder 2. So our molecular formula for this structure would be C9H11Cl with an IHD of 4. With an oxygen, it would be C8H7ClO with an IHD of 5. And with 2 oxygens, it would be C7H3ClO2 with an IHD of 6. If instead I thought there was nitrogen, 1 wouldn't work, but adding in 2 nitrogens would give me C7H7Cl N2 with an IHD of 5. This is a really powerful tool, friends. Most of the time you won't need it because you'll be given the molecular formula, or at least the elemental analysis you can use to find the empirical formula. But if you're really not given any information about the molecular formula, this is a really nice trick to have up your sleeve. What's your favorite spectroscopy trick? Let me know in the comments below, and if it's a really good one, I might pin your comment. Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.